We're waiting for him to set up. All right.
Okay. Hello, everyone. My name is Antonio Tanis. I'm a Master of Applied Sciences candidate at Ryerson University in Toronto, Canada. And I'm here to talk to you today about heat transfer to a moving wire in a gas fluidized bed furnace. Before I proceed, I'd like to let everyone know this is still a work in progress. We don't have results quite yet. Okay. That looks like that's going to stay there. Alright, so the motivation for this study, steel wire is a very useful part of today's society. Quite a few things are made from it. You have nails, wire hangers, springs, any sort of wire rope. You can even make a wire mesh with fences and things like that. For almost all of these applications, wire needs heat treatment. It's far too brittle after production to be used. So depending on the kind that you have, either low carbon steel or high carbon steel wire, the process is different. In the case of low carbon steel, it's a straightforward and fairly forgiving process, but high carbon steel requires very precise heating rates and stringent temperature controls. Typically, molten lead-based furnaces are used in this application. They offer very high heat transfer rates, however they're quite harmful to both the operator and environment. And for this purpose, they've been banned in many jurisdictions and require very expensive environmental controls to operate in others. We propose using a fluidized bed furnace, which is quite environmentally friendly. It is still quite thermally efficient. However, not much is known about the heat transfer rates to very small diameter cylinders, such as wire. I'm going to talk to you a bit about how wire is made. Usually, the process begins with a higher diameter rod, which is passed through several dies to reduce its diameter until it ends up as wire. This process causes quite a bit of work hardening, and as I mentioned previously, the wire is extremely brittle. So here I've shown as an example the heat treatment for high carbon steel wire. It's a process called packaging, and it involves heating the wire to 800 degrees Celsius, and typically a direct fire furnace, which is very thermally inefficient. And then it is quenched in a molten lead furnace at 480 degrees Celsius, and then soaks in another molten lead furnace. Now, we propose replacing all of this with fluidized bed furnaces. The advantages being improved thermal efficiency in the case of the direct fire furnace, and greatly improved environmental effect in the case of the molten lead ones. So I'm not sure if everybody's quite familiar with what a fluidized bed is, so I'm just going to tell you a bit about it. It's essentially a dense packing of solid particles that is suspended by fluid, and it has fluid-like motion. It's kind of in between. It's not quite one, not quite the other. It's made up of a vessel or container where you keep your particles. The particles themselves, you need a distributor for the fluid because you don't really want just a single jet blowing in the middle. And then the fluid itself at sufficient velocity and mass flow to be able to suspend the particles. Now, if you were to take this and add a heat source, you would end up with a fluidized bed furnace. Okay. So, since pictures are worth 1,000 words, I'm not too sure how much a video is worth, but I guess a lot. This is the fluidized bed operating in our laboratory. This is a sand particle-based fluidized bed, fluidized by air. you're seeing here is bubbles that form at the base of the distributor, growing, coalescing, and then bursting the surface. So, heat transfer, which is the main thing that I'm here to talk today about. There are three modes of heat transfer that occur to an immersed surface in the fluidized bed. You have particle convection, which occurs in the thin gas lines between the particle and the surface itself. There's the gas convection, which is the standard force convection that I'm sure we're all familiar with. And there's radiation, which occurs with the neighboring particles. All of these three can be summed to provide an overall heat transfer coefficient, but the contribution of each really depends on a lot of factors like the particles themselves, the flow conditions, and other parameters like temperature and pressure. A bit of background on these. So fluidized beds aren't really a new thing. Actually, just yesterday there was a keynote speaker that was talking about using fluidized bed as a catalyst for burning coal. That's a very common application for them, as well as in the power generation industry. They use them to transfer heat to boiler tubes. Those are quite large diameter tubes, so most of the studies have been done to large surfaces such as that. There was an excellent review paper by Saxena in 1989 that went over such correlations that have been developed and found that the correlation developed by Gromall and Saxena managed to predict all of the experimental data up to that point within a range of plus minus 15%. This is a really good result. However, a more recent study by my supervisor, Dr. Friedman, found that when you take these correlations and attempt to use them on very small diameter cylinders, like in the 1 to 7 millimeter range that we're studying, they grossly overpredict heat transfer, and even the nature of the correlation doesn't, the shape doesn't match. There was a correlation developed specifically for small diameter cylinders in this work. However, that work and all the previous had focused on static surfaces, which are just immersed into the bed. However, typically in industry, they use a continuous process, which involves many strands of wire just feeding through the furnace and being heat treated in that manner. So for this reason, we decided to develop what I believe is the first moving wire heat transfer rig. So what we have here is a view of our apparatus. It consists of quite a few components. There are two spools driven by 3/4 horsepower electric motors and controlled by variable frequency drives. There's a bunch of tensioner and guide pulleys to ensure that there's no slip and the wire doesn't go where it shouldn't. There's a wire traversing system. This is quite common in industry, and it's used to ensure an even and smooth deposition of the wire onto the collection spool. We have a pair of rolling contact thermometers, which are specifically designed to work with a moving wire. And we have a wire straightener, because when the wire pays off at the source spool, it does have a bend to it, and it needs to be rectified before experiments can occur. And finally, there's the source spool itself, which contains the wire. It has a brake on it, which ensures that it doesn't freewheel and lose tension. So there are quite a few challenges when designing something like this. One of the key issues is the wire speed. Since it is the parameter that we're studying, it's very important that we can keep it constant and we accurately know what it is at all times. For this purpose, we use the two-spool arrangement as opposed to a single, because when you coil a wire onto a spool, the diameter increases, and over time the linear speed of it would increase. What we've done is we have just a single turn of wire and a tensioning system to ensure it doesn't slip on the driving spool, and then everything else is taken up by the collection spool. In addition, there's a digital tachometer which tracks along the driving spool, monitoring the speed at all times. Another issue with wire is, I'm sure a lot of people have encountered this, it does tend to tangle and catch and make all sorts of unruly messes. For this purpose, we've trapper system, which again we can adjust to the wire, to the wire diameter, and it is synced to the drive speed because it runs off of it fully. So you get smooth and even wire deposit onto the collecting spool. And finally, when we initially attempted this, we used optical thermometers. They use infrared to measure the wire temperature, but we found them to be inconsistent on a day-to-day basis, even in calibration. We were getting different values on different days, so we decided to take a set of thermometers that were specifically designed for use with moving wire. Unfortunately, these only arrived just before the conference, and that's why there's no data to present today. I have a video here of the entire thing running in our lab. I'm just going to play that. And what you can see here is you can see the controllers there with the motors. Then that's the wire traverse right there, with two prongs guiding the wire along the spool. As you can see, it's depositing quite smoothly. There's no tangles or looping or anything like that. It's driven right off of the spool with a belt and pulley system. And there you see the driving one itself. And there's the digital tachometer that I mentioned. It's constantly tracking onto it. And that single turn of wire is kept in tension using these tensioning pulleys. That's a shot of the old optical thermometers. As I said, we're not using those anymore, but the mount we will reuse. They were USB enabled, so we're just data logging onto a pair of laptops. They required one laptop each. Since the first video, I've added two measurement thermal probes. They're both measuring the bed temperature. However, one is for data logging purposes. The other is for the temperature controller. It checks the bed temperature and then adjusts the heater accordingly. So this is the second laptop, which is now no longer in use. We switched to a data acquisition unit, which can measure from 8 different thermocouples onto one computer. And this is the inlet of the old thermometer. Currently, the heater was not running for this video. It has quite a bit of thermal mass, so it takes a very long time to heat up. So for the purpose of the video, we didn't run it hot. This is the wire straightener. It's an industrial wire straightener. It's just straight from the wire. And that is the source spool, where it all begins. Okay, so that kind of covers the experimental portion of it. At this point, when we complete it, we would have an inlet and an outlet temperature, as well as the bed temperature. From this, we have to turn to some models to determine what the heat transfer coefficient actually is. What we have here is a control volume of wire. And there are a couple of things acting on it. Since it is a moving wire, there is advection, and there's also conduction along the wire itself. Finally, the parameter that we're interested in is the convection, and that H there is the combined coefficient that covers the particle convection, gas convection, and radiation. If we take these, we can represent them as a differential equation, and we can make a simple substitution there for solution. We've solved this using Maple with the following boundary conditions. It's quite tedious to do by hand. What we have is the inlet of the bed is set to the measured inlet temperature, and at the outlet we have the slope of the temperature to be constant. After solving this, we end up with a very long and difficult to work with analytical solution. It would take up an entire slide, and it's tons of exponents, so it requires quite a bit of computational power. For this purpose, we developed a numerical solution as well. It involved taking the same differential equation and applying central differencing to the diffusion term and second order upwinding to the convection term. This gives the following discretization. When we compared the analytical and numerical solution, we found that the discrepancy between them was almost non-existent. So for this purpose, we chose to continue with the numerical solution because it is far easier to work with. It's very light computationally. The computer can chuck through it in a couple of seconds. So what we do with this is we take it and we test different values of H until the calculated outlet matches the experimental outlet, and that's how we know that we have the correct value for H. Finally, a bit more about the apparatus. It is designed only for low temperature operation. There's a reducer section installed on it where we operate the fluidized bed, and that one was made to ensure that we have adequate fluidization velocities. Also, we're using an electric heater, so it's really not capable of very high temperatures. But we're typically running at about 60 degrees Celsius, which gives us a large enough range between the inlet and outlet temperatures that we can develop get accurate results. Though the system is capable of handling wire in the 1 to 7 millimeter diameter range, which is perfect because that's really the only range we're interested in. And the blower has a 220 meter cubic an hour capacity, which is not an issue because we've designed the reducer specifically so that this blower will give us a very wide range of fluidizing velocities. Finally, the wire speed that the system is able to produce is 120 meters per minute, which is in line with industry operation, and essentially doesn't represent the issue. To summarize, we've built and tested a fluidized bed furnace. We built and tested a laboratory scale wire movement system. We've used a combination of spools, pulleys, straighteners, and trappers to ensure that the speed is constant and there's smooth operation with no variation in speed. And we developed an analytical and numerical model for calculating heat transfer coefficient. In the future, we need to calibrate and install the new thermometers that we've received and repeat the experiments at different diameters of wire and different speeds, because those are the parameters that we're interested in. Finally, I'd like to thank my supervisor, Dr. Jacob Freeman, who's in the audience here today, my co-supervisor, Dr. David Naylor, who's unable to attend, the support staff of the Mechanical and Industrial Engineering Department, Joseph Emmerkraut, Grace, and Roy Sherman, who helped me all throughout this endeavor. And finally, Ryerson University, the Faculty of Engineering, the Natural Sciences and Engineering Research Council of Canada, and Wire Kerner for generously providing funding for the study. Thank you, and I'm ready for questions at this point.
Unfortunately, we have to stop the question. We'll finish early today. Thank you very much, Antonio. Maybe you can talk to Antonio during the lunch hours. Our next speaker is